Scientists choose the model that best answers the question they are posing. VSEPR theory for one about molecular shape, or valence bond theory for the one about orbital overlap. But neither model adequately explains magnetic and spectral properties, and both understate the importance of electron delocalization. To deal with these phenomena, which involve molecular energy levels, chemists apply molecular orbital theory, which we call MO theory. Here in this yellow box, I have the Lewis structure for oxygen, O2, and there's nothing wrong with this Lewis structure. Both of the oxygens have an octet, and it has a double bond, which is consistent with the bond order of oxygen. The problem is, if we take liquid oxygen, you can see in this picture here that we can suspend liquid oxygen between the poles of a very strong magnet. That tells us that oxygen, O2, must have unpaired electrons because it is paramagnetic. But that's not consistent with the Lewis structure that I have in the yellow box. There are no unpaired electrons. And one of the things that we're going to see with molecular orbital theory is that we're going to be able to rationalize not only the bond order of O2, but we're going to be able to rationalize the fact that it is paramagnetic. The molecular orbital model is a quantum mechanical treatment for molecules similar to the one for atoms. Just as an atom has atomic orbitals of given energies and shapes that are occupied by an atom's electrons, a molecule has molecular orbitals, or MOs, of given energies and shapes that are occupied by the molecule's electrons. There is a key distinction between valence bond and molecular orbital theories, shown here. Valence bond theory pictures a molecule as a group of atoms bonded through overlapping valence shell atomic and/or hybrid orbitals occupied by localized electrons, whereas molecular orbital theory pictures a molecule as a collection of nuclei with orbitals that extend over the whole molecule and are occupied by delocalized electrons. Despite its usefulness, molecular orbital theory has the drawback that molecular orbitals are more difficult to visualize than the shapes of VSEPR theory or the hybrid atomic orbitals of valence bond theory. Just as the Schrödinger equation gives only approximate solutions for any atom with more than one electron, determining the molecular orbitals of even the simplest molecule, H2 or hydrogen, requires an approximation. The approximation is to mathematically combine, add or subtract, atomic orbitals, which are atomic wave functions, of nearby atoms to form molecular orbitals or molecular wave functions. Thus, when two hydrogen nuclei lie near each other, their atomic orbitals overlap and they can combine in two different ways. We can add the wave functions together. This combination forms a bonding molecular orbital, or a bonding MO, which has a region of high electron density between the nuclei. Additive overlap is analogous to light waves reinforcing each other, which makes the amplitude higher and the light brighter. For electron waves, the overlap increases the probability that the electrons are between the nuclei. This figure shows waves being added together, and we can see that we have an increased probability that electrons are between the nuclei. We can also subtract the wave functions from one another. This combination forms an antibonding MO, or antibonding molecular orbital, which has a node, a region of 0 electron density between the nuclei. Subtractive overlap is analogous to light waves canceling each other. With electron waves, the subtractive overlap means the probability that the electrons lie between the nuclei decreases to 0. If we combine two hydrogen atoms to make an H2 molecule, there are two possible combinations for the hydrogen atoms. We can either add them together to form a bonding molecular orbital where there's more electron density between the nuclei, or we can subtract them to form an antibonding molecular orbital where there's less electron density between the nuclei. Notice that the number of atomic orbitals combined always equals the number of molecular orbitals formed. We're adding 1, 2 atomic orbitals together, and we're forming 1, 2 molecular orbitals. The bonding and antibonding molecular orbitals have different shapes and energies. Here we can see the orbitals for hydrogen. A bonding molecular orbital is lower in energy than the atomic orbitals that formed it. Because the electron density is spread mostly between the nuclei, nuclear repulsions decrease while nucleus electron attractions increase. Moreover, two electrons in this molecular orbital can delocalize their charges over a larger volume than they could in the two separate atomic orbitals, which lowers electron repulsions. Because of these electrostatic effects, when electrons occupy this molecular orbital, the hydrogen molecule is more stable than the separate hydrogen atoms. And you can see that with respect to our potential energy, that the energy of the bonding molecular orbital right here is lower than the energy of the two separate or isolated hydrogen atoms. An antibonding molecular orbital is higher in energy than the atomic orbitals that form it. With most of the electron density outside the internuclear region and a node between the nuclei, nuclear repulsions increase. Therefore, when electrons occupy this molecular orbital, the H2 molecule is less stable than the separate hydrogen atoms. Both the bonding and antibonding molecular orbitals of hydrogen are sigma molecular orbitals because they are cylindrically symmetrical about an imaginary line between the nuclei. The bonding molecular orbital is denoted as a sigma 1s. That is a sigma molecular orbital derived from 1s atomic orbitals, and antibonding orbitals are denoted with a superscript star, sigma 1s star here, the antibonding molecular orbital derived from 1s atomic orbitals. For atomic orbitals to interact enough to form molecular orbitals, they have to be similar in energy and orientation. The 1s orbitals of the two hydrogen atoms have identical energy and orientation, so they interact strongly. We'll revisit this requirement for molecules composed of many electron atoms. Several aspects of molecular orbital theory, filling of molecular orbitals, energy level diagrams, electron configuration, and bond order relate to earlier ideas. Electrons enter molecular orbitals the same way they do in atomic orbitals. The molecular orbitals are filled in order of increasing energy, which follows the Aufbau principle. A molecular orbital can hold a maximum of 2 electrons with opposite spins, following the Pauli exclusion principle, and orbitals of equal energy are half filled with spins that are parallel before any of them are filled. And this obeys Hund's rule. In terms of molecular orbital energy level diagrams, a molecular orbital diagram shows the relative energy and number of electrons for each molecular orbital as well as for the atomic orbitals from which they are formed. In the molecular orbital diagram for H2, 2 electrons, one from each atomic orbital of hydrogen, fill the lower energy bonding molecular orbital, while the higher energy antibonding molecular orbital remains empty. Just as we can write the electron configuration for an atom, we can write one for a molecule. The symbol of each occupied molecular orbital is written in parentheses with the number of electrons in it as a superscript outside. The electron configuration for H2 is sigma 1s2. In a Lewis structure, bond order is the number of electron pairs per atom-to-atom linkage. The molecular orbital bond order is the number of electrons in bonding molecular orbitals minus the number in antibonding molecular orbitals multiplied by a half. A little bit more about molecular orbital bond order. If the bond order is greater than 0, the molecule is going to be more stable than the separate atoms, so it will form. For H2, we have 2 electrons in a bonding molecular orbital. We have 0 electrons in the antibonding molecular orbital. 2 minus 0 multiplied by a half gives you a bond order of 1, which is consistent with the single bond between the 2 hydrogen atoms in H2. If the bond order equals 0, the molecule is as stable as the separate atoms, so it will not form. And finally, in general, the higher the bond order, the stronger the bond is. One of the early successes of molecular orbital theory was its ability to predict the existence of He2+, the helium molecule ion, which consists of 2 helium nuclei and 3 electrons. Let's use molecular orbital diagrams to see why He2+ exists, but He2 doesn't. In the He2+, shown on the left, the 1s atomic orbitals form molecular orbitals. We have He2+. Remember that helium has 2 electrons, right? It has a configuration of 1s2, but we have a +1 charge, so we're going to remove one of those electrons. So we're going to have 2 electrons for one of the helium atoms, and one of them we're going to remove one of the electrons, so we only have 1 electron there. So those 3 electrons are distributed as a pair in the sigma 1s molecular orbital and a lone electron in the sigma star 1s molecular orbital. The bond order is a half because we have 2 electrons in the bonding orbital minus 1 electron in an antibonding orbital, and we multiply that by a half. So 2 minus 1 is 1, and multiply that by a half, and we get a half. So that's how we calculate our bond order. Thus, the He2+ ion has a relatively weak bond, but it should exist. Indeed, this species has been observed frequently when helium atoms collide with helium+ ions. The electron configuration of the He2+ is going to be sigma 1s2, sigma star 1s1. In He2, with 2 electrons from the sigma 1s and 2 electrons from the sigma star 1s molecular orbital, both the bonding and antibonding orbitals are filled completely. Stabilization from the electron pair in the bonding molecular orbital is canceled out completely by destabilization from the electron pair in the antibonding molecular orbital. So when we calculate our bond order, we have 2 electrons in the bonding molecular orbital, 2 electrons in the antibonding, and we multiply that by a half. Well, 0 multiplied by a half is going to be 0. And so we have a bond order of 0, and this proves or shows why a covalent He2 molecule doesn't exist. Let's try a problem. Use a molecular orbital diagram to find the bond order and predict whether H2+ exists. If it exists, write its electron configuration. Here's my molecular orbital diagram. I'm going to combine 2 1s orbitals. I'm going to make a more stable sigma 1s bonding molecular orbital, and I'm going to have a less stable sigma star 1s antibonding molecular orbital. How many electrons do I have in H2+? Well, I know that for every hydrogen atom, I bring 1 electron, right? Because hydrogen has an electron configuration of 1s1. But if I have 2 of them, and then I have a positive 1 charge, that means that I've lost an electron. So overall, I only have 1 electron. And that 1 lone electron is going to go into my bonding molecular orbital. So when I want to calculate my bond order, I'm going to take the number of electrons in my bonding molecular orbitals, which is 1, the number of electrons in my antibonding molecular orbitals, which is 0, and I'm going to multiply that by a half, and I get a bond order equal to a half. And so H2+ should exist. And the electron configuration for H2+ is simply sigma 1s and 1, like that. Homonuclear diatomic molecules are composed of 2 identical atoms. In addition to H2 from period 1, you're familiar with N2O2 and F2 from period 2 as the elemental forms under standard conditions. Others in period 2, like Li2, Be2, B2, C2, and Ne2, are observed, if at all, at high temperatures. We'll divide them into molecules from the S block, groups 1A and 2A, and those from the P block, groups 3A through to 8A. Both lithium and beryllium occur as metals under normal conditions, but molecular orbital theory can examine their stability as diatomic gases. Dilithium, which is Li2, and we have its molecular orbital diagram here on the left, and diberyllium, and we have its molecular orbital diagram shown here on the right. These atoms have electrons in inner 1s and outer 2s atomic orbitals, but we ignore the inner ones because in general, only outer or valence atomic orbitals interact enough to form molecular orbitals. Like those formed from 1s atomic orbitals, these 2s atomic orbitals form sigma molecular orbitals, cylindrically symmetrical around the internuclear axis. If we look at Li2 or dilithium, the 2 valence electrons fill the bonding sigma 2s molecular orbital. shown right here. And they have opposing spins, and they leave the antibonding sigma 2s molecular orbital completely empty. The bond order is, we have 2 here minus 0 multiplied by a half, which gives us a bond order of 1, shown right here. In fact, dilithium has been observed, and it has an electron configuration of sigma 2s 2. In diberyllium, the 4 valence electrons fill both the sigma 2s and the sigma star 2s, so both the bonding and the antibonding are filled. And so our bond order is going to be 2 electrons in our bonding molecular orbital, subtract 2 in our antibonding, multiplied by a half, which gives us a bond order of 0. And so diberyllium has never been observed. In boron, the atomic 2p orbitals are occupied. Recall that p orbitals can overlap 2 different ways, which correspond to the 2 ways their wave functions can combine. They can either overlap end-to-end, which gives us the sigma 2p and the sigma star 2p, or they can overlap side to side, which gives us the pi 2p and the pi star 2p. Despite the different shapes, molecular orbitals derived from p orbitals are like those from s orbitals. Bonding molecular orbitals have most of the electron density between the nuclei, and antibonding molecular orbitals have most of it outside the internuclear region with a node between the 2 nuclei. The order of the energy levels for molecular orbitals, whether bonding or antibonding, is based on the order of atomic orbital energy levels and on the mode of the p orbital overlap. Molecular orbitals formed from 2s orbitals are lower in energy than molecular orbitals formed from 2p orbitals because 2s atomic orbitals are lower in energy than 2p atomic orbitals. Bonding molecular orbitals are lower in energy than antibonding molecular orbitals. A sigma 2p is lower in energy than a sigma star 2p, and a pi 2p is lower in energy than a pi star 2p. Atomic p orbitals overlap more extensively end-to-end than side-to-side. Thus, the sigma 2p bonding molecular orbital is lower in energy than the pi 2p molecular orbital. We also see that the destabilizing effect for the sigma star 2p molecular orbital is greater than that for the pi star 2p molecular orbital. Thus, the energy order for molecular orbitals derived from 2p orbitals is typically sigma 2p, pi 2p, pi star 2p, and sigma star 2p. Each atom has 3 mutually perpendicular 2p orbitals. When the 6p orbitals in 2 atoms combine, the 2 that interact end-to-end form 1 sigma and 1 sigma star molecular orbital, and the 2 pairs of orbitals that interact side to side form 2 pi molecular orbitals and 2 pi star molecular orbitals. Placing these orientations within the energy order gives the expected molecular orbital diagram for p block period 2 homonuclear diatomic molecules, shown right here in A. Recall that only atomic orbitals of similar energy interact enough to form molecular orbitals. This fact leads to 2 different energy orders. Without mixing of s and p orbitals, O2, F2, and Ne2, the order in figure 11.21a assumes that s and p atomic orbitals are so different in an energy that they do not interact. We say the orbitals don't mix. Lying at the right of period 2, oxygen, fluorine, and neon are relatively small. Thus, as electrons start to pair up in the half-filled 2p orbitals, strong repulsions raise the energy of the 2p orbitals high enough above the 2s orbitals to prevent orbital mixing. Thus, the energy order of the molecular orbitals derived from the 2p orbitals is as expected for oxygen, O2, fluorine, F2, and dineon, Ne2. And so this order is only going to apply to O2, F2, and Ne2. When we have mixing of s and p orbitals for B2, C2, and N2, or diboron, dicarbon, and N2, nitrogen, The boron, carbon, and nitrogen atoms are relatively large, with 2p atomic orbitals only half filled, and so the repulsions are going to be weaker. As a result, orbital energies are close enough for some mixing to occur between the 2s of one atom and the end on 2p of the other. The effect is to lower the energy of both the sigma 2s and the sigma star 2s molecular orbitals, and to raise the energy of the sigma 2p and the sigma star 2p molecular orbitals. The pi molecular orbitals aren't affected. The molecular orbital diagram for B2, C2, and N2 thus reflects this mixing. The only qualitative difference for the molecular orbital diagram from O2, F2, and Ne2 is the reverse in energy order of the sigma 2p and the pi 2p molecular orbitals, which follows this order that I have shown in green right here. This figure shows the molecular orbitals, electron occupancy, and some of the properties from B2 through to Ne2. The first thing you probably notice is that higher bond order correlates with greater bond energy and shorter bond length. You can see that as we go from a bond order of 1 to 2 to 3, what happens? The bond energy increases. It goes up from 290 to 620 to 945, and then of course if it goes down to 2 to 1 it starts to drop again. So again, higher bond order corresponds to higher bond energy. It also corresponds to shorter bond length, right? You see that the higher the bond order is, the shorter the length is. The lower the bond order is, the longer the length is. The next thing you probably notice is that orbital occupancy corresponds or correlates with magnetic properties. Remember in chapter 8 that if a substance has unpaired electrons, it's paramagnetic and it's going to be attracted to a magnet. If all the electrons are paired, the substance is diamagnetic and it is not attracted to a magnet. The same distinction applies to molecules. Let's take a look at the molecular orbital occupancy and some of the properties. If we look at B2, it has 6 outer electrons. 4 fill the sigma 2s and the sigma star 2s molecular orbitals. The remaining 2 electrons occupy the 2 pi 2p molecular orbitals, 1 in each orbital, in keeping with what? Hund's rule. With 4 electrons in bonding molecular orbitals and 2 in antibonding molecular orbitals, the bond order is going to be 4 subtract 2 multiplied by a half, which gives us a bond order of 1. And as is expected, diboron is going to be paramagnetic. If we look at C2 or dicarbon, we have 2 additional electrons that are going to fill the pi 2p molecular orbitals, which is going to render it diamagnetic. It also has a bond order of 2, and so the bond is going to be shorter and stronger than the one in B2. If we move up to N2, you see that we have 2 more electrons that fill the sigma 2p, and so the molecule is going to be diamagnetic. It has no unpaired electrons. It also has a bond order of 3, which is consistent with the triple bond in the Lewis structure of N2, right? If we draw the Lewis structure, so that works out. If you look at O2, which is the next one on the list here, this is where you really see the power of molecular orbital theory over valence bond theory. In fact, it shows that we have a bond order of 2, which is consistent with the Lewis structure for O2 that we had drawn earlier on, right? We drew this Lewis structure, and there's nothing wrong with that Lewis structure. But molecular orbital theory also shows us that it has unpaired electrons, and it explains why O2 is paramagnetic. Lastly, you can see that fluorine has a bond order of 1, which is predicted by the molecular orbital diagram. And finally, if you work out the bond order of neon, you'll see that it has a bond order of 0 because all of the bonding and the antibonding molecular orbitals are completely filled, and therefore that explains why Ne2 doesn't exist. Let's try a problem. It says here, explain the following data with diagrams showing the occupancy of molecular orbitals. And so we're going to compare N2 with N2 plus, and then we're going to compare O2 with O2 plus. And you see that the trend here is that when we go from N2 to N2 plus, we end up decreasing the bond energy, so we get a weaker bond and the bond length increases slightly. When we compare O2 and O2 plus, we actually increase the bond energy, so we get a stronger bond and the bond gets shorter. And so our plan is going to be as is outlined right here. The data here show that removing an electron from whether it's N2 or O2 has opposite effects. N2 plus has a weaker and longer bond than N2, but O2 plus has a shorter and stronger bond than O2. We're going to determine the number of valence electrons for all of the species. We're going to draw the sequence of molecular orbital energy levels, showing orbital mixing for nitrogen, but not for oxygen. And then we're going to fill them up with the electrons. We're going to calculate the bond orders. We're going to see how the bond order relates directly to bond energy. Higher bond order means stronger bond, and inversely to bond length. So higher bond order gives us a shorter bond. Now nitrogen has a total of 5 valence electrons, so N2 should be 5 times 2, which gives you 10. And N2 plus, we subtract an electron because we have a +1 charge, has 9. If we fill up those molecular orbital diagrams for N2 and N2 plus, remember we have to show the orbital mixing, and we calculate the bond order for N2, we see that it has a bond order of 3, and the bond order for N2 plus, is shown right here, is 2.5. Does that make sense based on what we see here? And the answer is yes. If the bond order for N2 is 3 and the bond order for N2 plus is 2.5, of course the bond energy is going to decrease, going from the bond order of 3 to a bond order of 2.5. And again, its bond order is inversely related to bond length. And since our bond order is decreasing, our bond length is going to increase. Now if we look at O2 and O2 plus, oxygen has 6 valence electrons, so 2 times 6 gives you 12 for O2. O2 plus, we have to remove one, and we have 11. Remember that these molecular orbital diagrams have no orbital mixing. We calculate the bond order for O2, and it has a bond order of 2, and we calculate the bond order for O2 plus, and it has a bond order of 2.5. And that makes sense. If we have a bond order of 2 here, for O2 and 2.5 for O2 plus, then that explains why its bond energy is going to be higher for O2 plus. And if the bond order is higher for O2 plus, that explains why the bond length is shorter. Nitrogen monoxide, or nitric oxide, is highly reactive because of its lone electron. 2 possible Lewis structures for NO with formal charges are shown right here, number 1 and number 2. Both structures show a double bond, but the measured bond energy suggests a bond order higher than 2. Moreover, it is not clear where the lone electron resides, although the lower formal charges for structure 1 suggest that it's on the nitrogen. The molecular orbital diagram shown here is asymmetric, with the atomic orbitals of the more electronegative oxygen lower in energy. When the 11 valence electrons fill the molecular orbitals of NO, the lone electron occupies the pi star 2p antibonding molecular orbital. 8 bonding and 3 antibonding electrons give a bond order of 2.5, right? Because we have 8 in bonding molecular orbitals, subtract 3 in antibonding, multiplied by a half gives us a bond order of 2.5. This bond order, 2.5, is more in keeping with the data than either of the Lewis structures. Bonding electrons lie in the molecular orbitals closer in energy to the atomic orbitals of the oxygen atom. The 2p orbitals of the nitrogen contribute more to the orbital that holds the lone electron, so it spends more time closer to the nitrogen. It's important to keep in mind that this diagram shows the energy order with the mixing of the 2s and 2p orbitals, as we saw before, but the result is the same with or without the orbital mixing.